Hey everyone, so we're on to the next topic, which is all about springs and swings. Now, we kind of already talked about springs, at least with the spring force, and we did also briefly mention the idea of the spring energy. It really is just a plug and chug with the spring energy. So, this is actually more focused on the concept of swings or pendulums, something that we haven't really talked about. So I just want to do a quick question. So pause the video where it's up. We'll go over in a second. All right. So this question, very typical. This is a conservation of energy question. You could do the 5 questions for this. You can do the idea that they only really mention 2 energies. So obviously they're going to be set equal to each other. But if you did the 5 questions, yes, there's a height change. It starts at a height, so it's going to start with potential. No, there's no speed change that we know of. It starts at rest, and by the time it lands on the spring, uh, the it goes back to being zero. There's no person applying a force to it. There's no friction, but there is a spring. So we end up starting with gravitational potential and going into spring potential. We set mgh equal to 1 fkx squared since they give us the masses and heights, what we can use to find potential, and they want to know about the spring constant. So we're going to need to plug that equation in for spring potential, plug our numbers in, chug out our answer, and we get 392 newtons per meter. All right, easy enough. Here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so this is another one where you could use the 5 questions. You could also use, we kind of talked about it briefly, but the flow of energy. So at the very bottom of the spring, when the spring is completely compressed, it basically has all spring potential energy. Once that spring releases the ball, that spring potential goes into kinetic energy at the very bottom of the ramp because it starts moving at some speed. And as it goes up the ramp, it starts losing this kinetic energy as it turns into gravitational potential. Because of the flow of energy going from spring potential to kinetic to gravitational potential, and there's no other forms of energy it could go to, we know that all these energies are equal to each other. Now, what this means is that if I want to know how much kinetic energy the ball has, I can either find this amount of spring potential that was stored in the spring or the amount of gravitational potential energy that it ends up having at the very top. Now, if I actually look at part B really quickly, part B ends up asking me what's the spring potential. So clearly, I can't be finding this to get A if I'm then going to have to find this after I get A. Kind of defeats the purpose. So that means we're probably going to have to look for this. And if I look at my variables, it makes sense. I have the mass, I have the height, and that's everything I need to know to do PE equals KE. So I do mgh equals KE. Again, I'm not solving the 1 half mv squared equation because I don't need to know anything about that. I just need the kinetic energy. So I plug my numbers in, and I get that the kinetic energy that I need is 0.196 joules. So the ball ends up gaining 0.196 joules of potential, which it had to have had the exact amount of kinetic in order to reach that height. And then when I get to part B, finding how much energy was stored in the spring, well, if the ball ended up gaining that amount of kinetic, it must have started with that amount of potential spring. This is the idea of conservation of energy and the flow of energy and all that stuff. We still only have 0.196 joules of energy. It's just changing forms from spring potential to kinetic to gravitational potential. And then with part C, how much does the spring need to compress? Now that I have the spring potential, I could do 1 half kx squared and do my plug and chug. And I end up getting 0.0626 meters or 6.26 centimeters. So this is just a little bit of practice using spring energy again. Remember, it's not super common that you're going to be seeing it a lot with conservation of energy, but it comes up enough where you probably should know about it. But the thing that I want to focus more on right now is swings. Now, this is still related to energy and conservation of energy. But it kind of has a second thing that's not super related to energy that we want to talk about. So, if you don't know, a pendulum or a swing is essentially a mass attached to a string, and that's it. It's allowed to hang from the string, and it basically just moves side to side, similar to what this pumpkin is doing in that animation, though most pendulums will just do it uh, repetitively. Uh, so, the some terms that we need to talk about. We had the mass, which is here. We have the string. We have the lowest point, which is usually we're going to call the 0 point. Basically, it doesn't matter how high this pendulum is off the ground. We're going to consider this lowest point as being the ground. Even if it was, on the top of a mountain, we would still consider the lowest point of the pendulum as the 0 point, the ground. Everything is going to be taken from this position. And then we have some fixed position here. A lot of times this specific point is going to be called the equilibrium position because this is where the force due to tension and the force due to gravity are going to be equal to each other. Hence the term equilibrium position. Also, when it stops moving, it's going to be at that location, kind of going back to the idea that that would be where it would be in equilibrium. All right, so here's the first question. Here, I just want you to try and describe the flow of energy. So try to talk about what type of energy the pendulum starts with, what does it turn into, all the way back until it reaches its original position. So pause the video, work itself, and we'll go over in a second. All right, so the flow of energy is potential to kinetic to potential to kinetic to potential. Now, to kind of illustrate this, in the beginning we had the pendulum raised at some height. It then flies down until it gets to that equilibrium point. This is where it has all kinetic. It's going to continue upwards to its highest point, where it begins to come back down and repeat the process. This time going upwards, back to where it started. So this is the pendulum. Kind of weird how it's drawn, but that's the idea. It starts at potential on the left side, let's say, comes all the way down to the bottom, goes all the way to the right up to some height again, so it's got that potential back, goes back to kinetic, goes back to potential as it returns. So the main idea with the pendulums is that it's a visual aspect of the transfer of energy from potential to kinetic and back and forth. The total energy of the pendulum does not change, but we have a constant changing between the types of energy. So yeah, it always ends up having potential at the top, kinetic at the bottom, and the mechanical energy is always going to remain the same because no energy is going to be lost to friction or heat, or at least in the ideal cases. So here is a question where we can do some practice. What you want to do is find the potential, the kinetic, and the velocity at all these 3 points. You can fill out this table to kind of visualize it a little better. So pause the video, work itself, and we'll go over in a second. All right. Now the first question asks, what's the potential energy? So at point A, it is 2 meters above. So I use PE equals mgh. Using these numbers, I end up getting 60 joules because it's 3 kilograms times 10 times 2 meters. At point B, it's at the lowest point. Now remember, this is where it has 0 height. So the height is 0, means the potential energy is 0. And then at point C, well, it's at the same height as A, and that's the only difference. That's the only thing that's going to be changing for the pendulum. So that means it's going to have the same gravitational potential as point A. So we have 60 joules, 0, and 60. Now, for the kinetic energies, what we're going to do is kind of look at this a little bit. So point A has no velocity. It starts at rest when it gets released. So that means all this energy is in potential. So that zero kinetic. Now, as it goes down to the bottom, it's losing its potential. It had 60 joules of potential, but then it went to zero. So where did all that excess energy go? Well, it had to have gone in the form of kinetic. So that 60 joules gets added to my initial kinetic, which means I now have 60 joules of kinetic. As it goes back up to this max height, it regains that 60 joules of potential, which means it must have lost all of its kinetic again. Now we can double check this because, as I said before, the total energy should remain the same. So if I add potential and kinetic for point A, I get 60. For point B, point C, it's 60, and point B, it's 60. So it's all 60. And that's the main idea, that the potential energy, the total energy is not changing. I could do the same thing if I wanted to know about some point here that's in between, maybe call it point D, and I figured out using MGH that the potential here was 20 joules. Well, because the total has to still be 60, that means my kinetic energy would be 40. This is how we use conservation of momentum. The idea that the total energy doesn't change, so it's getting split between potential and kinetic in some way. I can then use the equation for kinetic energy, 1/2 mv squared, in order to find the velocities at all the points. When at point A, it's got 0 joules, so it's 0 meters per second. Point B, when I plug the numbers in, I get 6.32 meters per second. And then point C, once again, it's 0 meters per second, since it has no energy. And that's it. All right. There's one last thing that I need to talk about. It's this idea about period. So pendulums have this very unique aspect to them, where they have a period that it takes for them to make one full swing. So that's a full swing is starting, let's say, at its height to the left, going to the other side, and then back. So as long as it returns back to where it started, moving in the same way, that is what we consider as one full swing. And the period is that amount of time. You can actually notice that it is a measurement of time, since it's given the letter T as a symbol, though it's a capital T, to kind of differentiate from other times, to say that it's a special time. So despite the fact that period starts with a P, we use capital T to show that it is a form of time. Now, what's special about this is, what are the characteristics that affect this period? So what about a pendulum can we change in order to change the period? Well, first we could ask ourselves, does mass affect the period? Does the length affect the period? Does how high we drop it affect the period? Or does gravity affect the period? So these are some common questions and common factors that we could change to change the period. But not all of them actually do. Like, for example, the mass actually has no effect on the period of the pendulum. You can change the mass for the most part, and it doesn't really do anything. The length, on the other hand, will actually affect the period. If we do change the length, it will change the period by making it longer. So the longer the string, longer the period. It has somewhat of a direct relationship in that sense that as one goes up, the other one goes up. And this does kind of make sense, since as the string gets longer, it's going to be covering basically a much longer path due to its longer length. Drop height, it's sort of not really. In this class, it's not going to be affecting the period. But in the real world, yes, it does sort of affect it, but not nearly as much as some of the other factors. So we actually say it still remains the same, though that's mainly true for smaller angles. So as long as we're not bringing it all the way to its highest point, like a complete 90-degree drop, essentially, the period shouldn't really seem that much different from small angles. And then the last factor, does gravity affect the period? Yes. Here, stronger gravity will give us a shorter period, which is essentially somewhat of an inverse relationship again. So that's pretty much it. That's this whole idea about pendulums. Like I said, the two aspects that you need to know are about the fact that It goes potential to kinetic, and that's the transfer. That mechanical energy is remaining constant throughout. And then the last thing is this idea about period, and that these are the factors that can or can't affect the period. If you have any questions, feel free to let me know. Otherwise, I'll see you later. Good luck and have a great day.